All right, Physics 11, welcome back to our discussion on projectile motion. All right, so far we've accomplished two of the four types of projectile motion that we can talk about. Like I said, in this course we're only going to deal with three, and the fourth type we will deal with next year. Okay, so the first one we've dealt with here is our vertical launch, where we're just throwing something straight up and watching it come back down. Or the vice versa of that one is if we say had something, say a person on a cliff, and we just drop that ball or rock or whatever it is off the edge and we watch that fall straight down. Okay, both of these are similar in that we are just dealing with that straight up and straight down motion, no horizontal. Then last week I introduced you to this setup here where we are on top of a building or a cliff or a bridge, some sort of elevated situation. And we're just launching something straight horizontal right off the top of this. Okay, so we're just in here launching it straight this way. And the motion we see is this kind of downward pull. Okay, now when we dealt with this one here, we want to separate our components into two pieces. We've got our horizontal motion, and then we've got that vertical. Okay, so when we're dealing with that horizontal motion, remember we're just dealing with the constant velocity situation. Okay, so that only leaves us with a couple formulas to deal with in that situation. However, in this vertical, just like we had the vertical over here, all we have going on is we're starting off with a zero vertical velocity, but we do have that acceleration due to gravity, and that's what's going to cause it to fall back down and form this shape. And we want to treat those two directions separately. Okay, so we're going to analyze in the horizontal position and in the vertical position, and just going back and forth between those two when we have our pieces of information that we needed. All right, just before we touch on the new one here, remember too, also we start off with a vertical velocity of 0, and we only have our horizontal velocity. Okay, so that's not same situation. Our new situation that we're going to be dealing with this week and next week is what I call this angled launch. Okay, we're going to be starting off at ground level, and we're just going to angle launch and watch it hit back to the ground. Okay, so in all of these, I've kind of drawn the cannonball situation. We can also think of throwing a ball, throwing a rock, any of those situations, and just remember we are ignoring air resistance. Okay, so we've dealt with these two, we're now going to deal with this one. Now for this situation here, we're going to get some sort of a initial velocity at some angle theta above the ground. Okay, so we're just going to use that angle theta here to help us. So the examples we have in the textbook, I'll look at or on the note sheet there. So the first one we have is we are launching something at 15 meters per second, 35 degrees above the ground. Okay, so we are told that our initial velocity is 15 meters per second at an elevation of 35 degrees. Okay, and so all that's going to look like is we're launching something in this situation, and we're going to look at this angle in here at 35 degrees. Okay, so we want to understand how we can deal with this. Now, once again, we are going to have constant velocity in the horizontal direction. In our x direction, we have constant velocity, so that simplifies our formulas. But we've got this change in velocity in our vertical, in our y direction, because of that acceleration due to gravity. Okay, so we're going to come back to this example here. We're going to have to decompose this into our Vix and our VIY, that initial y value and that initial x value. Okay, and so that's where that vector information that we dealt with before spring break is going to come into play. Okay, Now, before we get into this, I'll come back to all this stuff. I just want to remind us of a few key characteristics of our projectile motion. All right. If we get here, let's call this the peak of our projectile. Okay, so we start off with down here. We have an upwards velocity and a horizontal velocity, and that's at our initial position. At this point here, we're going to have a little bit of a vertical still, and we're going to have that same horizontal. Hopefully those are both the same size for you. Okay, when I get to this peak, it's come to the top and it's going back down. Now, if we're thinking about our vertical, an object goes up, momentarily is at rest, and then starts accelerating down. Well, that's what we're having here. Now, we have no vertical velocity, but we're still going to have that same magnitude of the x. Remember that x is not changing throughout this whole process. Okay? If I come into a point, that was at that point, and that was at the initial. If we come to this point, similar height, but still on the way back down, we're going to have this little arrow velocity going in the downwards direction, and we have that constant x direction. And then when it hits the ground, we still have that velocity in the x, and now our y direction velocity is going to be the same magnitude as when it was launched, but in the opposite direction. Okay, so we just want to understand a little bit about those velocities. Now, we also mentioned how this forms a parabola. Okay, and so if it's forming a parabola, the time it takes to go from when we launched it to our peak is the same time as to go from our peak back down to the ground. Okay, we have that constant change of velocity in the vertical direction, or that constant acceleration due to gravity. So whatever the time it takes to reach your peak, it's the same time it takes to reach back down to the ground. Similar when we're throwing something just straight up and straight down. Okay. One other thing that we want to talk about is we're going to talk about that height at the peak. Okay, so that height at that peak, that is this piece here. Okay, we usually abbreviate that as the y or the dy. Okay, talking about the distance in the y direction, how high we can reach in the y direction. And then we also talk about the range or the horizontal distance. And so that's going to be from launch point to end point. And that's just going to be that x direction in or x displacement, okay, in that horizontal. Okay, so those are the ones we're going to take. Now, to figure out the height of the peak, we're going to use the time to get up to that point. To figure out our range, we're going to need to find the entire time that we're in the air. Okay, and so that's what we're going to start off with today. I'm going to start off with questions 1, A, B, and C, just how to decompose those vectors. Actually, I'm going to do A, because we're going to come back to doing those vector breakdowns in question 2, and I'm going to cover 2A, B, and C, and then I'll leave you guys to check out the rest of that worksheet. Okay, so looking at question 1A on that angled launch worksheet. All right, we have an initial velocity of 15 meters per second at 35 degrees. So whenever we're dealing with these, we can just draw that initial vector as a right triangle. And it's this right triangle that's going to help us to be able to solve all of these problems. All right, now when we've drawn this out, we've always said that our x is our horizontal, so I'm going to label that here as our x. And then we always say that our y is our vertical. So I'm going to separate that into these two situations. Okay, now let's take a look at this x direction first. Okay, I have my hypotenuse, I have an angle, and the way I've got this out here, my x is my adjacent. So I could write that out and say that my cosine of 35 degrees equals my adjacent over my hypotenuse. Okay, so if I want to rearrange this to solve for x, my x is going to be that 15 times the cosine of 35 degrees. From here, we just plug that into our calculator, and this is now going to give us that Vx, right? We started with an initial velocity, so our initial velocity in our x direction is then going to be 12.287 meters per second. Okay, so in a lot of these problems, we're going to be starting off with this VI x and the VI y, or that initial x and initial y velocities. And we're not really too interested in what those are per se, but we're going to use those in further calculations. So I'm probably going to use that number as we move on. But if that was the only question, was wanting to know that initial launch velocity, make sure we pay attention to sig figs. We have 2 in our data. So we're going to have that initial x velocity of 12 meters per second. Okay. Now, similarly, if we want to solve for our y value, based on the way that we've drawn our triangle, we have our angle, we have our hypotenuse, and we have the opposite side. Well, in that case, then we're now going to be dealing with the sine of 35 is equal to that y over the 15 meters per second. Okay, and so then I can rewrite that as y is equal to 15 times the sine of 35. Again, into our calculator. I get 8.6036. Our units here, meters per second. Okay, so that means then our Vy, our velocity in that y direction, is then, 8.6 meters per second. And remember, that one we can definitely give a direction to of up. This one here, based on the way I've drawn this, I guess I can call that to the right. Okay? But that's essentially what we're going to be doing for a lot of these problems. We're going to take some sort of initial velocity at an angle, decompose that vector into its x and y components. Okay, and if we draw our pictures and we're very careful with our pictures, we're going to get up a situation where our x is the magnitude times the cosine of the angle, and our y is the magnitude times the sine of that angle. Okay, so you might want to pay attention to the wording here, and then just remember to have those in here. And it's always good to draw a picture for these. All right, so the rest of question 1 was just practicing that decomposition. If you take a look at the worksheet on Schoology, you'll also notice that the answer key is posted on a file there as well, and you can double check that work. Now, I'm only showing the one example on breaking down that vector, because in these next 3 that I'm going to do, we're going to have to go through that initial state as well of decomposing this vector. So, first thing we're looking at here is we have this initial velocity, okay? And I can then take a look here. If I'm going to look at my Vix, right, that initial velocity in the x direction, I'm going to take my magnitude, my 30.0 meters per second. I'm going to multiply that by the cosine of the angle provided, which happens also to be the 30 degrees. Okay, entering this into my calculator, I come up with a value of 25.981 meters per second in the horizontal direction. Okay. If I then look at my VIY, again, we're going to take that magnitude, that 30 meters a second, and this time though it'll be the sine of that 30 degrees. Okay. And this will give us our value of 15.0 meters per second. Although we'll be using all 5 sig figs to do any future calculations, and we're going to do that for most of these problems. Most of these problems are going to have 2 or 3 sig figs in our data, and so we are going to give our answers to the appropriate sig figs. But while we're carrying out our calculations, I usually stick with 5 sig figs. Okay? It's 2 or 3 more than whatever we're provided, and that is usually a safe buffer zone to make sure there's no rounding errors. And so this one, it is 15 on the dot. This one, though, we have that 25.981, so I should approximate that then as, once I round this, to be 26.0 meters per second. Okay? Now, keep in mind that we were starting at 30 degrees, so we're launching at 30 degrees above the horizontal, right? We're always dealing with these positive directions for this course, so we don't have much to worry about there. And that means that our initial y velocity then is also going to be in that positive or in that upwards direction. Okay. All right, just need a little more space to solve the rest of these questions here, so I just rewrote those velocities at the top. Okay. Now, a third piece of information that we need, or an additional piece of information that we've got to take from these problems, is that our x is going to be constant, right? Our velocity in the x direction is always constant. However, we have that acceleration in the y direction of a negative 9.81 meters per second squared. Okay. We're, for this course, launching in a vertical direction, so our gravity is in the downward direction. So I have my positive for my velocity, I have my negative for my acceleration. Okay, now, next up on this list, and the order that we solve these usually follows the way that we have that list that's on there and the way that I'm doing these, whether that's a word problem or an example like this. So the next thing we need to find is the time to go up, okay? And we want to remember that, as if we're just throwing this vertically, ignoring the horizontal for section, if something goes up, reaches the peak, and then comes back down, momentarily at that top section, the final velocity is going to be 0, okay? So for this situation, we can use this formula that the VF equals VI plus acceleration multiplied by time. And now that is that time up, okay? And so if we're looking at this, as it comes to the top, it stops and comes back down. Well, that means that this piece here is always 0, okay? And so I'm going to bring this VI to the other side. So I've got a negative VI equals acceleration multiplied by the time up. Okay. And so then my negative VI divided by that acceleration equals my time up. So in this case, I have a negative 15.0 divided by a negative 8.1. Okay. And when I plug that into my calculator, I get a value here of 1.5291 seconds. Okay. And this formula is going to work out very well pretty much all the time we have to do these time up, because we have an initial velocity in the y direction, we have an acceleration in the y direction, and at that peak, we know that this is 0. So that gives us enough information, so we can start shortcutting this to be that the time up equals that negative VI over A. Okay. So that was our time up. Our time total is just going to be 2 times the t up, right? Because the time it takes to reach that peak, the time it reaches back down to the ground, it's always just going to be twice that value, because we're starting from the ground and we're coming back to the ground. Okay, just rather than straight up and straight down, we're just going to do something like that. Okay, but it's always going to come back to the ground. So whatever the time it is to reach the peak, it's double that time to get back to the ground. And so for this example, that gives us 3.0582 seconds. Okay, I just rewrote those values up at the top, and again, keeping in mind that if we're doing these to 3 sig figs, to make sure we round these off to 1.53 and 3.06. Okay, Now, these next two questions, the order you do those in is arbitrary because they are separate. Okay, so if we're going to take a look at the way it is on there, we want to find that maximum height. Okay, so that maximum height, that dy. Okay, well, to find this one, we need to use the formula that the distance or displacement equals that VIY, the initial y velocity, multiplied by the time up. Right, and I say just the time up because we want to know how far it goes on the way up to that maximum peak, so I need to know that time at the peak. And then from here, plus 1/2 AY times T up squared. Okay? So in this problem, the reason we started in the order that we do is because to get this this distance in this direction here, I need to use this initial y velocity, which I have up here. I need to use this acceleration that I have right here, and then I need to find or use this time up here and here from this value here. Okay, keeping in mind that it's this time up that's squared, not the whole portion at the end. Okay, so what I'm going to have here is my dy, my displacement in the y direction, is going to be that 15.0 multiplied by that 1.5291 plus 1/2 times the negative 9.81. Remember, these are in opposite direction. Our velocity initial was in the upwards direction, our gravity's in the downwards. We need to make sure that we have those opposite signs. And then 1.5291 squared. Plug that all in. I get a value of 11.468 meters, which is approximately 11.5 meters when we consider sig figs. The last question on there is to figure out the range. Okay, so this is our x direction, so we're looking at that displacement in the x direction. And because we have constant velocity, our distance here is just going to be that Vix, okay, that velocity in the x direction at the initial, multiplied by the t total. Okay, it goes up to the peak and comes back down. It's in the air that entire time, so we need to use that total velocity, or sorry, total time. And so for this problem then, I'm going to use my 25.981 multiplied by my 3.0582, and that leaves me with a range or a horizontal displacement of 79.455 meters, which again we will round off to be 79.5 meters. Okay, hopefully that helps. Let's get around to some summarizations here, and then we'll move on to B and C. Okay, so just a quick summary here. Our Vix is going to equal whatever that initial velocity we have times the cosine of the theta that we are provided. Our Viy is going to equal that initial velocity magnitude times the sine of the angle that we're provided, so that's sine theta. When we are looking for that time in the upwards direction, just like I manipulated that formula before, we are going to have that negative Viy divided by the A. Okay, but we want to be careful here. A is negative 9.81 meters per second squared. Okay. Then when we got to figure out our time total, it is just double the time up. Our dy, our maximum height, okay, this is that VIY multiplied by the time up plus 1/2 A in the y direction T up squared. Okay, just remember that A is negative, so this whole piece here will be a subtraction. And then the nice and easy one is once we've figured out our total time and our initial x velocity, we can find the range as that Vix multiplied by the total time. Okay, now I know we've got a lot of formulas on those sheets. We've worked through a lot of formulas in those past few units. These are the culmination, or the using all of those in certain orders in certain situations to be able to find out all these different pieces. Okay, now rather than manipulating those formulas every time, I suggest you write these down on your formula sheets. You use them as you work through these problems, and feel free to use those on the tests and the quizzes when they come up. All right, moving on to question B, 2B that is. We're going to follow a similar format. I'm not going to write out as many steps in this one, but I'm just going to kind of talk our way through the process as we write these out. Okay, so we're starting off with this 30.0 meters per second at an angle of 45 degrees. Okay. Our Vix is going to be that 30.0 times the cosine of 45, and I get 21.213 meters per second. If I look at my VIY, 30.0 times the sine of 45, I also get 21.213. Okay. The only time these two values, our x and y direction, are going to be the same is when we're at that 45-degree angle. Okay, it's very important to remember that. Anytime you see the 45, you'll have the same Vix and the same VIY. Okay, so now that we have those, we can continue on. We can find that our time up is equal to that negative VIY divided by A. So my 21.213 divided by 9.81, and I get 2.1624 seconds. My time total is just 2 times that upwards velocity, so I end up with 4.3248. Okay. Now, my dy, this is the one that's that very lengthy formula. So we're going to have that Vy times the time up plus 1/2 A T up squared. Okay, so this part here is going to be the 21.213 multiplied by 2.16 plus 1/2 times the negative 9.81 times the 2.1624 squared, and from here I get a value of 22.935 meters. So our object on the way up takes just over 2 seconds to reach just under 23 meters high. When I look at the range, or the x displacement, I just have that initial x velocity multiplied by the total time. Okay, so my 4.3248 seconds times the 21.213 meters per second, and I end up with 91.742 meters for my range. Okay, so on the way up, the object spends just over 2 seconds to reach 23 meters before coming back down. In the xward direction, it is in the air for over 4 seconds and then travels 91.7 meters. All right, last example, we're going to take a look at 2C, where we are given that initial velocity of 30 meters per second at an angle of 50 degrees. Okay, so our Vx is our magnitude times the cosine of the angle, 19.284, whereas our Vy is 30 times the sine of the angle, 22.981. Okay. Now that we have that initial velocity in the y direction of 22.981, I can divide that by my acceleration, and I get 2.3426 seconds. My time total is double the time up. Okay, so 4.6852 seconds. Solve our maximum height, or our height at peak. We need the initial velocity upwards, the time to go upwards, and then our acceleration due to gravity. We plug all those values into this equation here. We get 26.918 meters. And then to find our range, or our distance in the x direction, we take our velocity in that x direction, multiply by the total time that we're in the air, and we end up with a range, or a horizontal distance, of 90.349 meters.
Okay, so that's our notes on projectile motion. Remember, we've got the two different types that we're dealing with. Well, technically three, although we're probably just going to stick with the two. The horizontal launch off of a cliff or a building, and then the angled launch from one point on the ground over here, up and back down to the ground on this side. Okay, that should be the only types of problems we have. You've got quite a few examples from last week and this week to help you with those. Make sure you work your way through those problems, check out any other worksheets you have, post some questions, ask me questions. I'll get back to you on office hours. And next week is mostly just going to be more review and practice, and probably going to be a brief online quiz for me to check how you guys are doing. And then the following week, I will set up our first actual test. But I'll make sure you guys get a chance to try a quiz on Schoology before you do the online version, or the full version of a test. Okay? Good luck. Thanks for stopping in.